to actually study the air conditioning system design, it's better if we just revise the psychrometric properties thoroughly, because those are the basics that will be required to solve the numericals in air conditioning system design. Okay. So today's lecture will be dedicated to the revision of psychrometric and psychrometric properties. So we'll proceed with that. Okay, so as you know already that psychrometry is the science of studying the properties of moist air. Now moisture is part of the other constituents of air. Now air consists of other constituents like nitrogen, carbon dioxide, etc. All those things are there. But from air conditioning point of view, the moisture plays an important role because human comfort, the moisture has a huge contribution. If you are staying in a very moist place, for example near a sea, and when it is summer, then the temperature is high. Also, the humidity levels are quite high. So, a normal human being will not be comfortable if he is in those conditions for a very long time. So, and additionally, moisture is as such water vapor. So, water vapor has a high amount of latent heat in that, and to control or to add or remove water vapor takes quite a bit of energy. So, it is very important to study moisture whenever we are doing air conditioning system design. Okay. So basically, as we have discussed before, air conditioning involves controlling the following parameters. The first one is temperature. That is the temperature of air that is surrounding any human being. That needs to be in a reasonable value so that the human body can emit or reject the heat that is being generated inside. Second is the moisture content, as we were discussing. Third is air distribution. Fourth is air velocity. Fifth is purity of air. So I'll be referring to my notes at the moment to just revise through the psychrometry. Uh, the first property that we had discussed was dry bulb temperature. It is the temperature of moist air measured by any standard thermometer whose bulb is not covered by anything but only exposed to moist air. The second one is wet bulb temperature, wherein the thermometer's bulb is covered with a wet cloth and it is exposed to a current of air. So that wet cloth, the moisture in the wet cloth is going to take away additional amount of heat, and the wet bulb temperature will be slightly lower as compared to dry bulb temperature. Now, the rate of evaporation again depends on the moisture content of air. So greater the moisture content of air, the rate of evaporation through the wet cloth will be slower, and hence the wet bulb temperature drop will be lesser as compared to dry air. So difference in both is known as the difference in between the dry bulb temperature and wet bulb temperature is known as wet bulb depression. And this wet bulb depression will be zero when the air is completely saturated. That means that the air cannot hold any more moisture. That means that the wet cloth is not able to give away or evaporate the water from the cloth, and hence the water won't vaporize and it is not going to carry away additional heat. Therefore, wet bulb depression is zero when the air becomes saturated. Next parameter is dew point temperature. Whenever you want to, whenever we keep a cold glass of any cold water on a table exposed to air, you will find that moisture condenses on its outer surface. That is when the moisture content in the air uh, comes out in the form of water droplets and it condenses out. So dew point temperature is that temperature at which moisture in the air begins to condense when the air is cooled. Okay. Next is specific humidity or humidity ratio. It is denoted by omega, and it is the ratio of mass of water vapor to the mass of dry air. Okay, so this is a very specific parameter whenever we are trying to define the humidity content of moist air. And in mathematical terms, omega is equal to mass of water vapor to the mass of dry air. And we also derived this expression in class, if you remember. Omega or humidity ratio is equal to 0.622 PV upon PT minus PV. I hope you remember what is PV, PT. Okay, I hope you
Yes,
all
sir.
remember
Yes,
what is
sir.
that, right? Okay.
Yes, sir.
Next parameter is relative humidity. It is defined as the ratio of actual mass of water vapor in a given volume to the mass of water vapor if that same volume of air is saturated at the same temperature. It is basically a comparison between a given volume of air having some amount of water vapor to that same volume of air if that air inside that volume is completely saturated. So it is going to give us a relative idea as to the given sample of air how saturated it is. Okay, so in most of the cases you would have seen in newspapers or lots of news channels wherever they are broadcasting the weather data, they will specify this ratio, this parameter, which is your relative humidity. Next parameter is the degree of saturation. It is the ratio of specific humidity of moisture, that is omega, to the specific humidity of saturated moisture. Okay, that means the water vapor content in a given sample of moisture to the water vapor content in a saturated moisture. And this is the formula to find the degree of saturation. Now, we had also proved that degree of saturation is equal to relative humidity when PVS is very, very small. So in most of the cases, degree of saturation is not extensively used. Relative humidity is the parameter which is more extensively used. Next parameter is the enthalpy of moisture. Now, as we know that moisture is basically dry air plus water vapor that is suspended or mixed with the dry air. So, enthalpy of moist air is the summation of enthalpy of 1 kg of dry air plus enthalpy of water vapor in that 1 kg of dry air. And this is the formula that we will be using. I'll explain the individual terms in those. CPA is the specific heat of dry air, which is taken around 1.2, and TdB is drivable temperature plus omega. Omega that we know is your specific humidity or humidity ratio. Then you have HGDP. Okay, it is the enthalpy of saturated vapor at dew point temperature. This you need to find from your steam tables. Next is CPV. This is the specific heat of water vapor. Okay, and next is TDV, that is driver temperature, minus TDP, that is dew point temperature. Next, we had seen what a psychrometric chart looks like. Now, I've intentionally put color-coded image over here so that we can have a better differentiation between the lines. Over here, your x-axis is your drivable temperature. Y-axis is your specific humidity or humidity ratio. Then these red lines that you see, those are your constant enthalpy lines. Now they also coincide with your wet bulb temperature lines. Okay. These blue lines that you see, they are your relative humidity lines. So as we go towards the left of the chart, the relative humidity goes on increasing till you reach the end that represents a 100% relative humidity line. And the green ones are your specific volume lines in meter cube per kg. So we can carry out these 7 psychrometric properties processes. First one is adiabatic mixing of two air streams. wherein the the resultant or the mixed airstream will have properties in between the two airstreams. If one particular airstream is having a greater uh, volume flow rate, then the resultant property will be closer to that airstream. Second psychrometric process is sensible cooling. Then we have sensible heating. Then we have cooling and dehumidification. And then we have cooling and humidification. Then heating and humidification. And then heating and dehumidification. So sensible cooling means, as the name suggests, we are just going to cool the given volume of air. Okay, in this case, we'll require a cooling coil, and the air is simply going to pass over that cooling coil. So, as you can see from the figure, uh, your air is at initially at condition 1. Okay, and as it passes over the cooling coil, it is being cooled, hence its driver temperature is being reduced to zero point 0.2. And over here, the cooling coil is at temperature T3. Now, in practical cases, the outcoming air is never going to achieve the temperature of cooling coil because of the fact that some amount of air is going to bypass the cooling coil, or it may happen that the air is not getting enough time for it to give out its heat to the cooling coil. So that brings us to a factor known as bypass factor. Okay, it is, if you recall, it is very much similar to the effectiveness of a heat exchanger, wherein the temperature drop that you get, it is divided by the maximum possible temperature drop. Same thing is over here. So bypass factor here is mathematically given as T2 minus T coil upon T1 minus T coil. So T2 minus T coil, that is T2 minus T3 upon T1 minus T3. Okay. So in this case, one thing to note here is that as the air is being cooled, its relative humidity goes on increasing, because we know that that is a fundamental property of air. As you cool the air, the moisture carrying capacity reduces, hence its relative humidity goes on increasing. Next, we can find the sensible heat removed or the cooling effect that is generated. It is nothing but the enthalpy difference, H1 minus H2. Okay, and when you multiply it with the mass flow rate uh, of the air flowing over the coil, then you get the total cooling capacity in kilowatts. When you divide that by 3.516, you get in tons. Is this clear? Is everyone understanding this?
Yes, sir.
Yes, sir.
Yes,
Yes,
sir.
sir.
Okay. Next process is sensible heating. It is similar to sensible cooling. Only difference is that you have a heating coil in place of a cooling coil. Uh, Here again, your humidity ratio or specific humidity remains constant because we are only adding heat and we are not adding moisture to the air. Okay, so air enters at T1 and leaves at T3, and the heating coil is at T2. Okay, so again, same thing applies over here also. The air is not going to achieve the temperature of heating coil because of again the bypass filter. So here the sensible heat added is Cp of air multiplied by the temperature difference, or in simple terms, H3 minus H2. Next process is cooling and dehumidification. This process is more specifically used for summer air conditioning, especially for the coastal areas wherein the temperature at during the summer is quite high, as well as the humidity is also quite high. So in this process, you have cooling of air as well as removal of water vapor from air. So as we know that to remove water vapor from air, the coil temperature should be below the dew point temperature at that condition. Okay. So whenever the air that flows over the coil, which is having a temperature below the dew point temperature, the water vapor will start condensing on the coil itself, will start forming droplets, and when those droplets coalesce or combine with each other, they will fall down, and you have removal of moisture or humidity from the air. Now, in your household ACs also, you must have seen that there is a pipe that comes out from the indoor unit, and you have water that is continuously dripping from that pipe. So that is nothing but the condensation that is happening. Okay. Uh, so process 1 to 2 over here is your cooling and dehumidification process. For this to happen, the coil has to be at the below the dew point temperature. Okay. So this process 1 to 2 can be split in two parts. 1 to A, which represents sensible cooling, wherein you don't remove any moisture, you just sensibly cool the air. And the second part is A to 2, wherein you dehumidify or you remove the moisture from air. Okay. And the enthalpy difference H1 minus H2 can again be written as H1 minus HA, which is the sensible heat that you're removing, and then you add it to HA minus H2, which represents the latent heat removed, wherein your humidity ratio goes from omega 1 to omega 2, okay, which causes the condensation of water vapor present in the air. So this again brings us to another term, and a very important term from air conditioning design point of view, which is your sensible heat factor. Okay, so this sensible heat factor is defined as the ratio of sensible heat to the total heat. Okay, total heat will of course have sensible heat plus latent heat. So this factor is extremely important because it is going to decide or give us an idea about the nature of uh, condensation that we want to bring about. For example, I will give you two examples. We have an auditorium and we have let's say a kitchen. So in auditorium, what happens is there is a large audience, of course, and they are seated. So the level of activity is almost close to, or it is, you can say it is negligible. Therefore, the perspiration or the latent heat addition is very, very small. So your sensible heat factor, in that case, since the latent heat is small, the sensible heat factor is going to assume or have a very large value. Okay, it will be close to zero point 0.9 or 0.85 or something. And if you have a kitchen wherein there is a lot of cooking that is being taking place and a lot of boiling is taking place, so naturally the cooking process is going to add a lot of water vapor into the room, and that is going to add the water vapor content. That means we are adding the latent heat into the room. Okay, because there is a change of phase happening, right? water the water that is being boiled gets converted to water vapor. So you're adding latent heat or change of phase a of the liquid is happening. So latent heat is being added. So the denominator will have a large value, and sensible heat factor will have a smaller value as compared to that for an auditorium. So this line that you see 1 to 2 will be more steeper for your kitchen case. Okay, so this will give the designer an idea about the nature of latent heat inside the room, which is for which the air conditioning system is to be designed. Okay, so if you see the psychrometric chart over here, the psychrometric chart on the right hand side has a sensible heat factor over here. I hope you are having your psychrometric charts in front of you, or you can refer to the screen. Uh, there is a sensible heat factor scale over here. Okay. So you can see over here that when your sensibility factor is close to 1, for example, if it is zero point 0.9, then the line is almost horizontal. As your sensibility factor goes on reducing, that means there is more and more latent heat that is supposed to be removed. Your line slope goes on increasing. Okay, so you need to understand how to use this scale properly. Okay, because this will be required when we are solving numericals on air conditioning systems. Okay, I hope everyone is understanding how to estimate the sensibility factor.
Yes, sir.
Okay.
Yes.
Next is cooling and humidification. This is also known as adiabatic cooling. So this process is used in again in summers wherein the outside conditions are very hot but dry. Now one example would be Delhi or Nagpur maybe, wherein the in summers the temperatures outside are very high, but the humidity levels are quite low. So you can say it is quite hot but dry air. Okay, in such situations, we simply use a spray of cold water. So what this cold water spray is going to do is it is going to cause cooling as well as humidification. Okay, so as and when the air is going to come in contact with this cold water spray, it is going to get cooled. As at the same time, the moisture content is also going to increase. Okay, so that is going to uh, decrease your dry bulb temperature but increase your humidity levels. Okay, this process is also used in air coolers. Now how many have air coolers at home?
Sir, how will moisture content increase?
Because the air is going to absorb that moisture, right? See, when the air is flowing over here and there is cold water spray, so air is hot, right? The air
Yes,
is
sir.
quite hot. The humidity levels are very low for air.
Low.
So the air is
Okay.
readily going to absorb the moisture from this cold water space. Okay, so as the
Okay,
water
sir.
is cold, the temperature is going to drop, but at the same time, the humidity levels will increase as the air is going to absorb the water vapor.
Okay, sir.
Okay, so how many are using air coolers? Anyone uses air coolers?
No, sir.
No one? Okay, all of them AC. All of them use ACs.
Zero.
Yes, sir.
Okay,
Yes,
Nirav
sir.
uses.
Yes, sir, no.
पंखा नीरव पंखा
सब जगह नीरव का ही तुम नाम डालते हो.
भाई यार
Sir.
ठीक है. ओके, अगर देखा रहेगा तुमने कभी तो
उसमें पानी
we
डालते हैं, right?
हाँ we add some ice
हाँ? हम्म.
and water in those air coolers. So what that is going to do is that you're essentially adding cold water to those air coolers, and there is a a belt, a conveyor belt is made of a fabric which is going to absorb that cold water, and air is made to pass through that fabric belt.
Sir, but if humidity ratio is high in air, then what will happen?
Sorry.
Humidity ratio, if humidity ratio is high in that air,
In the incoming air.
yeah, yes,
Then you will not use this process, no. See, this process is used only in the case where the air is very much dry and but it is very hot. Okay, if it is having a lot of humidity content, then you will use cooling and dehumidification. Understanding?
okay, yeah,
So
yeah, sir.
this process is in particular is used in places where it is very dry and very hot. Okay, if you have been to Nagpur or interiors of Maharashtra, there वो बोलते हैं ना लू लगता है.
पेंट
So in
Dry heat.
yeah, it is dry
पेन
heat.
पेन में
Huh. It is very dry heat. So in such situations, you need to add moisture, little bit moisture, so that an average human being will feel comfortable. Okay. So next process is heating and humidification. this is essentially used in winters, wherein the temperatures go very low and almost there is negligible moisture content in the air. So it is fairly simple. You have a heating coil and you have a spray of water. So your process 1 to 2 is going to represent heating and humidification. Again, you are adding sensible heat from 1 to A, and then you are adding latent heat from A to 2. So if we are to represent all these psychrometric processes that we have discussed on your psychrometric chart, this is how it will look. Okay, now you should be able to draw this diagram. Even अगर रात को नींद से उठा है तो भी ये तुम्हें draw करने आना चाहिए, because this understanding is extremely important. Without this, you should not proceed to air conditioning system design. Okay.
Yes, sir.
Yes, sir.
So we had solved a
sir.
few numericals.
Yes, sir.
We had solved a few numericals using the analytical method, wherein you will be using only formulae to solve, and the other was the graphical method, wherein you will be using a psychrometric chart to solve. Now, in the exam, the question will specifically mention that तुम्हें chart use करना है या analytical method से solve करना है. Okay. Now, do I need to revise these things?
Yes, sir.
Okay. So here in this case, the question says that yes, what happened?
सर ये पीवी पीटी पीडब्ल्यू ये क्या है, मैंने मिस कर दिया था, प्लीज
Okay.
एक बार बता दो ना.
Okay.
ये सब में ही बता दो.
Okay. So PT is nothing but the total pressure of air. Okay. Total pressure of air. PV is the partial pressure of water vapor. Now air will consist of lot of components, and all of those components will have some partial pressure. Okay. So for water vapor, that partial pressure is represented by PV. Okay. So here this question says that the psychrometer reads 40 degrees dBT and 28 degrees WBT, and assuming that the barometric pressure is 1.013 bar, determine these things. So here 1.013 bar is your total pressure. Okay, PT. Okay. So humidity ratio is given by this formula. Omega is equal to 0.622 PV upon PT minus PV. Now here we need to first find PV. So PV is partial pressure of water vapor. But for that, to find PV, we have to use this Carrier's equation. Now please note, you will have to remember this equation. Okay, ये equation तुम्हें याद रखना है. So
Yes, sir.
PV is equal to PW. Okay, PW is saturation pressure corresponding to the wet bulb temperature. PW minus PT minus PW into brackets T dry bulb minus T wet bulb upon 1544 minus 1.44 T wet bulb. यहाँ पे तुम्हें सब values input करने हैं. Now to find PW, okay, you will have to use steam tables. और steam table में जो saturation pressure रहेगा at this wet bulb temperature, that is going to be your PW. So you
साइकोमेट्रिक चार्ट से ही आता है ना पीडब्ल्यू.
हाँ, साइक्रोमेट्रिक चार्ट से नहीं, साइक्रोमेट्रिक चार्ट के वहाँ पे उसके पहले एक टेबल है.
हाँ, एक टेबल है. हाँ.
उसमें ये तुम्हें पूरा वैल्यूज मिल जाएगा. So whatever the corresponding temperature and saturation pressures, all those values are given in that table. So according to Carrier's equation, you will have to input these numbers over here and
Sir,
find
steam table से
steam table में भी है,
steam table से
but there's no need to carry steam table, but you will require steam tables to find the enthalpy. Enthalpy में HF, DP, HGDP का एक value है, so steam table में से ही आएगा.
सर
Yes,
ड्यू
sir.
पॉइंट टेम्परेचर फाइंड करने के लिए भी लगे सर.
हाँ, वो ड्यू पॉइंट टेम्परेचर के लिए वो साइक्रोमेट्रिक चार्ट के वहाँ पे टेबल है, उसमें मिल जाएगा. So here you will input these numbers and find PV. Okay, so PV comes out to be around 0.03 bar. So simply you substitute this PV back here in this humidity ratio का formula, and you will find your omega value. Okay, omega comes out to be 0.019 kilogram of water vapor per kilogram of dry air. Okay. Next, we have to find the relative humidity. Relative humidity is the ratio of partial pressure of water vapor to the partial pressure of saturated air. Okay, now PVS is saturation pressure of water vapor corresponding to the dry bulb temperature. अब इसका मतलब क्या है? This means that the moisture holding capacity of any volume of air is governed by the dry bulb temperature. अगर ये dry bulb temperature बढ़ गया, means that air can hold even more water vapor content. So that is the reason why the PVS, that is the partial pressure of saturated air, is always corresponds to the dry bulb temperature. So from steam tables or the tables behind the psychrometric chart, you can simply find the partial pressure at
Sir,
dry
can
bulb
you repeat the
temperature.
previous statement about PVS?
Okay, PVS means what? It is the partial pressure of saturated air. Okay, partial pressure of vapor corresponding to the dry bulb temperature of, that is here it is given as 40 degrees. So
Hmm.
the moisture holding capacity will depend on the dry bulb temperature. अगर तुम्हारा dry bulb temperature air का ज़्यादा हो गया, so that means that the air can hold even more amount of moisture.
Moisture.
Okay, so
Okay.
PVS always corresponds to dry bulb temperature.
Dry
So
bulb temperature.
from those tables, you will find the partial pressure at 40 degrees Celsius. It comes out to be around 0.07375 bar, and simply you will substitute here. You will get the relative humidity as 40.7%. Dew point temperature, it is the saturation temperature corresponding to the partial pressure of water vapor. Okay, so अब water vapor का क्या pressure है? PV है, right? So जितना water vapor रहेगा उतना ही condense होगा, right? So condense, that means dew point temperature. So dew point temperature always corresponds to PV. Okay, so from those tables we'll again look up for the value of dew point temperature corresponding to the partial pressure of water vapor, which is PV. From tables you will find that dew point temperature comes out to be around 24 or 24.5 degrees Celsius. Next is the enthalpy of the moist air. Here you will use this formula that we were discussing just 15 minutes back. In this case only you will have to find HFGDP. Okay, this value you will get from the steam tables at the dew point temperature. That is the latent heat at the dew point temperature of 24 degrees. इसमें से तुम्हें find करना है. That value comes out to be around 2445 kilojoule per kg, and you can substitute the remaining values and you will get the enthalpy as 88.42. Okay, so just to cross check our values, we can simply open the psychrometric chart and see what the values are. Okay, in this case 40 and 28 degrees Celsius, 40 dBT and 28 degrees Celsius WBT. So 40 and 28. So that comes out to somewhere over here where my cursor is. Okay, so we can verify our values. We were getting enthalpy at around 88. Okay, and here also 28. So here also the enthalpy that we are seeing in the psychrometric chart is around 90, somewhere around 88, 89, 90. So we can ensure like this that our calculations are correct. Okay. Uh, Next is a numerical that we had solved using the psychrometric chart. Okay. Now in this case, we had solved this numerical wherein there was sensible heating that was taking place. Uh, Volume flow rate is given as 1.2 meter cube per second. The dry bulb temperature initially was 15 degrees Celsius at 90% relative humidity, which was sensibly heated to dry bulb temperature of 50 degrees, 50 degrees Celsius. So we had to find the heat added, specific humidity, and the new relative humidity with the help of psychrometric chart. So you will have to plot these points on the psychrometric chart. First point is where your dBT is 15 degrees Celsius and relative humidity 90 degrees. Okay. So since it is a sensible heating, it will be a horizontal line till the dry bulb temperature of 50 degrees Celsius. Okay. So here you will read the enthalpies at all the properties at point 1. Enthalpy at point 1 is around 40.5. Specific volume at point 1 is 0.83 meter cube per kg. And omega 1 that you read from the axis, it is the y-axis, it is around 0.0098 kilogram of water vapor per kilogram of dry air. And when you are able to plot point number 2, you can read the enthalpy as 77.5 kilojoule per kg. Okay. Now, since volume flow rate is given, we'll have to find the mass flow rate. Okay, mass flow rate is given as volume flow rate divided by the specific volume, of course at point number 1. So when you divide volume flow rate by the specific volume, you get mass flow rate as 1.445 kg per second. And we know that the heat added is mass flow rate into the enthalpy difference. We get the heat added as 53.465 kilowatts. Specific humidity that is going to remain constant since it is sensible heating. It is around 0.0098 kilogram of water vapor per kilogram of dry air. Relative humidity at point number 2, you will have to find this relative humidity line that passes through this point number 2. Now ideally the relative humidity lines are in the range of 10%, 20%. So it will lie in between 10 and 20. So you'll have to approximate a little and you should get relative humidity as 12%.